So why do we call it the periodic table? The reason why is because as we line up the elements in a line, periodically certain patterns come up as you look at their chemical reactivities. Let's take an example of one of these. Let's say we were to look at all the elements in the first 41 and ask which ones reacted violently with water. You get those right there. Notice it's not a really perfect pattern, but there's definitely some pattern that's happening. Something's happening periodically within those first 41 elements. If I was to ask a second question of which ones do not react with any elements, I could look and I get this pattern. So notice it's a little different than the pattern above, but it's pretty similar. So periodically, certain things happen if you line up the elements according to their atomic mass. The first person to develop this concept of the periodic table was Dmitry Mendeleev. He put all the elements in order of their atomic mass, but then put them in groups by their chemical reactivity. He used atomic mass for his periodic table. Henry Moseley came along and he decided that atomic mass didn't work out for everything, so he ended up putting them in order of atomic number. Mendeleev got most of the credit for the periodic table. In fact, he's considered the father of the periodic table because although not very many people believed that he was right in his way, he predicted where several elements would exist once we discovered them. And when it turned out that he was right, they gave him all the credit. So let's look at the periodic table and make sure you understand some of the categories and names we give to certain situations. The first one's groups. Groups go up and down. You'll notice there are 18 groups on our periodic table. There's two little rows down at the very bottom that you see there. They are found within that periodic table and just taken out for a couple of reasons you'll find out later. Periods go across, and you'll notice there's 7 periods that go across the periodic table. And remember, those two at the bottom are taken out of rows or periods 6 and 7. There's 3 major groups of elements that we talk about on the periodic table. The first one's called representative elements, and they are represented by groups 1, 2, and 13 through 18. They're representative of most of the elements you'll talk about in our everyday routines. The next group is called the transition elements or transition metals, and it's in groups 3 through 12. These are called transition elements because they transition between more than one charge. Sometimes they can have a +2, a +3, or even sometimes a +1, or all the way up to +5, +6. The last group's known as the intertransition metals, and the reason why they're called that is because they are within the transition metals, so we call them the intertransition metals. There are some common names we give to groups just so we can refer to them in an easy manner. Group 1 is called hydrogen and the alkali metals. Group 2 is called the alkaline earth metals. Group 17 is called the halogens, and Group 18 is called the noble gases. Down in the intertransition metals, you'll see that the top row is called the lanthanide series, and the bottom row is called the actinide series. The periodic table also has a diagonal line that separates our metals from nonmetals. Those elements that are to the left of the diagonal line are considered metals. Those elements to the right are considered nonmetals. The elements I have listed here in pink that touch the diagonal line are called semimetals or metalloids. Metals like to lose electrons, nonmetals like to gain electrons, and semimetals can behave sometimes like a metal and sometimes like a nonmetal. This section deals with the blocks of the periodic table. Remember, there were 4 different types of sublevels or shapes of orbitals. These same letters are going to denote what we see on the periodic table in the blocks. The first block we talk about is the S block. The S block, as you notice, contains 2 columns. And if you remember correctly, the S sublevel had 1 orbital which could contain 2 electrons. It's no accident that there are 2 columns and 2 electrons in the S sublevel. The next block is the P block. Remember, the P sublevel had 3 orbitals which could hold 6 electrons, so it's no accident that it contains 6 columns. The next block is the D block. The D block contains 10 columns, groups 3 through 12, also known as the transition metals. Notice it has 10 columns, and there were 10 electrons you could fit in the D sublevel. The last block on the periodic table is the F block. You'll notice it has 14 columns in it, representing the 14 electrons that can be found in the F sublevel. So let's keep in mind those blocks of the periodic table, and also remember the Aufbau principle, something you remember as the diagonal rule, in order to figure out electron configurations using the periodic table. If we look at the first element up in the top left, which represents hydrogen, and since it's in row 1, or period 1, we consider its highest level of electron to be in the 1s sublevel, and since it's only one column over in that S block, we consider it to be 1s1. If you look at helium on the right, you'll notice it's 1s2. That is not in the S block, but its theoretical placement could be right next to hydrogen, and it represents 1s2. That's really our only tricky one of the periodic table. As we increase the atomic number, the next block we come to on the periodic table is 2s. Notice there are 2 columns in the 2s block. The first one would be 2s1, the second would be 2s2. As we increase atomic number, we go to 2p. Notice there are 6 in there. That represents 2p1 through 2p6. Then we go 3s, and then it goes 3p. Keep increasing atomic number. The next one we come to is 4s. Now, if you remember from your Aufbau principle, the next energy level higher than 4s is 3d, and then becomes 4p, and then becomes 5s, and then becomes 4d, and then becomes 5p. And that keeps going. Just remember that the D block is always one behind the S and the P. If you have 4s, the next level is 3d. If you have 5s, the next level is 4d. Let's do the noble gas configuration for niobium. If I go to the row above it and go all the way to the right, I can get its noble gas inner core. That would be krypton. That krypton in brackets takes care of all the inner shell electrons all the way up to number 36, krypton. So the only thing we need to write out after krypton is what is left after that element. So the first level we come to is 5s, and we have to go through both columns to get through that 5s to get to niobium. So we would write 5s2. Remember, the next block we get to is 4d because the d's are always one behind. So we get there and we have 3 that we need to go over in that 4d block to get to niobium. So I would write 4d3. And that's how you do the electron configuration in the noble gas configuration. A lot easier than writing it all out.